smiling. How are you, lovely gentleman and lady? That's good. Do you love my picture? Of me in my older days? Before I passed away. Good morning, good sir. Welcome. Please, have a seat. Well, we're getting ready for people to come. Would someone like to be a volunteer?
Yeah.
Please, come up, sir.
All right. There's a smile underneath this.
That's good. Here, I'm going to give you a measuring cup, but made by my famous people called pirates. Can you get me a half of a cup of hot water? There's some around the corner. Thank you. Good morning, good sir.
Good day, madam.
And who do we have online? We have a Stephen Taylor. Very good name.
Thanks.
We will begin in a minute when my volunteer returns. My name is Julia Child, by the way. Oh. Nice to meet you all, yes. Again, this is me and my younger self, me and my older self, when I was on PBS. Go watch me, I have lots of episodes. I like to drink or fine wine, but they told me no wine on campus today. Unfortunately. Make sure you have lots of butter with all of your things that you eat. Tastes better with butter. Shall we wait a few more minutes? We only have one on our online system here. For those of you that are here, I will announce that online you can download a document that's called Concrete Mixture Proportioning. Your instructor would like you to have a copy of this. We will be walking through it today. And there's a second one which might be nice to download at some point, which we'll also be doing today, which is called Mixed Design Example 2020 _ blank .xlsx. Welcome. Good morning. We'll begin shortly when my volunteer potentially returns. Good morning, everyone. Please have a seat. Oh, I'm so glad there's so many of you today. I love my hair too. Oh, good. My volunteer has arrived.
This is not as hot as our campus really.
Thank you. All right, shall we begin? Yes? Okay, ladies and gentlemen. My name is Julia Child. I am a reincarnated version in a younger self with concrete everywhere. Someone stuck me in a concrete world. I think I should have been in the culinary arts, but somehow I'm here. So I did the best I could. If you don't know me, go home and watch PBS and you can watch my older self. Today, we are going to do Mastering the Art of Concrete Cooking. Yeah? Your instructor has told me that you should be reading chapter 7 of your book. They did provide me with your book so you can see it too. Chapter 7. Now, today, there's lots of details. There is a document online you can go look at. I have shown the other fellows and ladies here that there's a document called Concrete Mixture Proportioning Example. We will be following this today. And then for your reference, there is the Excel version, which is called Mixed Design Example 2020_blank.xlfx. Woo. All right, we will be going through those later. And I'm told what we don't get to today, you will cover on Thursday with your regular instructor. All right? Now, if anyone has a problem with my accent, you can raise your hand and say, I have a problem with your accent. I have no idea what country it comes from. I've traveled all over the world. But we will get going. So, today, you are to learn how to do a concrete mixture. Right? There are 3 methods, I am told. Now, I am a fan of number 3. But we will go through them. Number 1 method is called the 3-2-1. Very easy to remember. I'm sort of a fan if you're in a pinch. Not a pinch of salt, but in a pinch. You can do this. It works. I call it the backyard method. When you're in your backyard and you want to make some concrete cookies, you go 3 scoops of, does anyone know? Sand and aggregate. And then you do 2 scoops of coarse aggregate. And then you do 1 scoop of cement. Now, am I missing an ingredient in my concrete cookies? Water. How much water do I put in? Anyone? That looks good. 2 scoops. Maybe not 2 scoops. Maybe a half. I don't know. You'd have to look at it. I like to look at it, policy. Look at it till it looks like the right consistency. Do you want a cake? Do you want a cookie? Yeah? Okay. Now today, the bulk of the work is going to be on the ACI method, which has been set out since the 1940s, when I was born. I think when I was born. Someone could Google when I was born. But anyway, that is considered the standard practice today. So we will go through it. Unfortunately, it's a recipe type, and I do not like recipes, as maybe you know, maybe not. I tend to follow roughly the proportions. So I tend to go with the volumetric method, which is where someone else gives me a recipe that exists, that they work really well, and I like to watch them, like my French counterparts. I watch them make it with all that butter. And I recreate it on my own, with my own flair. I would highly encourage that method for things like your high-strength competition, which I will be here to support you for if you need it. Any questions on the methods? All right, before we get going, I think it's time to do a demonstration. And we are going to raise the screen because it's more fun. And because I have so much energy today, we are going to do an activity. Because I like cooking, we're going to figure out how to cook today. Did you know you're coming to cook? All right. Let's make to make some concrete cookies. So we will make both today, virtually. How do I make cookies? What ingredients do I need?
Water.
And flour.
Butter.
Butter. Everything's better with butter.
Sugar.
We need some sugar. My man Justin over here has lots of sugar, I guess. What else? Eggs! Oh, excellent! Eggs! Other ingredients? Baking powder or soda? Baking soda powder. What else?
Chocolate chips.
Oh, I love a good chocolate chip. Ooh, some vanilla flavoring. I'm gonna run out of space here. Vanilla. Good flavors, good flavors. Anything else in your cookies? We're missing a little bit of that pinch. The salt. The salt. Where do you put it here? Did you know there's salt in your cookies? Makes it taste better. Just like butter. Okay, anything else? Do I need water for my cookies? Okay. How about concrete? What do I need in my concrete? Ooh, good. Aggregates. Yes. Find a marker that works. We have a coarse and a fine. Do I need both in coarse and fine? Depending on what I want it to look like. Just like I mentioned that backyard concrete. Do I want a cookie or do I want a cake? What else do I need in my concrete? Cement. Alright, anything else? Water. Okay. And I could put what? What admixtures do you want in there? Water reducer. Let's put it as a big category here. Admixture. We have water reducing admixtures. I meant fly ash. Is that an admixture, a cement? Fly ash. Anything else? Polymers. What kind of polymers? Fibers. I can put some fibers in. Does anyone like carrot cake? Those have great fibers in them. Long, stringy carrots, good for the diet. Anything else? Air. Oh, we like light and fluffy. Who likes air? We like angel cake style, right? Air bubbles. I think that's good. Let's figure out if there's similarities. What is an aggregate in my cookie? My chocolate chip. Is my sugar an aggregate? Or does it mix in? I put it dissolved. I like to eat it in one bite. How about cement? What is that in a cookie? added whites. How about that butter? That's kind of weird. I think that's part of our cohesive glue. All this cement. Now let's get to the other ones. Vanilla. Vanilla is an admixture. How about this salt? I'm going to say that's an admixture. Don't need it, makes it taste better. Do I need butter? Yes. Do I need baking soda or powder? Do I always need it? Maybe not. There's different types of cement in the baking world. Right? Depending on your altitude when you're baking. Do I have an equivalent for fiber over here? My carrots, come on, carrots. All right, carrot cookies. How about fly ash? Can I do different types of flour? Can I do different types of butter? Different types of sugar? Yes. There's another analogy I'm going to bring up. We can also make oatmeal. Who likes oatmeal in the morning? Oh, good. We got some takers. I went over to Winco and bought a big oatmeal. I personally like aggregates like blueberries in my oatmeal. Don't need them. I can just go with a paste mixture of oats. And you can get saccharate of oatmeal. How does this work? Today's lesson is not what are the ingredients, but how do I proportion it? Who here has ever made oatmeal that was not the right proportion? Yes. Okay. Let's make the right proportion. Would you like the same volunteer, or does someone else want to volunteer? Huh? Come on up, volunteer. If you're volunteering, you can even get to eat it.
Oh,
By the way, I have a few more.
yes.
Would you like blueberries?
I love blueberries.
All right.
Antioxidants.
Let's put it in a bowl. Now this is my saccharate. So someone else sat here and figured out the right amounts of the oats. And by the way, that's like a flour. We'll even put it up here for you.
There we go.
There you go. All right. Thomas, who has brought in the ingredients, gets to figure out the magic amount. How much water should he add?
Anyone want to guess?
Now here's a question as he's pouring. Oh, go ahead.
There is a thing on the back of the package.
Oh, but you put the packet away
In my pocket.
in your pocket. And I even have a spoon if you'd like a spoon. Now there's another thing I'm going to mention that happens with concrete and concrete cookies and concrete oatmeal. The temperature. When the room temperature or the water temperature is cold, is it easier to mix or harder to mix?
When it's colder?
When it's cold, it's hard to mix.
Right.
If that temperature is hot, the room temperature or the water temperature, it reacts faster, but it also dissolves faster.
Good mixing.
So one thing that they've done at the Oats Company is they figured out you can put it in the microwave to go faster.
Have to look.
And I think that's pretty good. What kind of consistency do we have here? Cookie. That's a good cookie. Very good cookie. Now what if I wanted some soup?
You have more water.
I have more water. You want your soup?
Let's do it. Let's add some more water to this.
It's up to you.
Let's get these things to
We
swell.
are always gonna add more oats too. All right. Thank you, Thomas. You can take it to your seat if you like it.
Sure.
Free breakfast. All right, let's go on into the ACI method. Oh, by the way, before you got here, I made up some of the oat concrete cookies. I put a little bit of less oats, more flour, some pumpkin, because I felt like pumpkin might be a nice admixture today, with a little bit of chocolate chips. If that's not the thing you like, that's okay. But in a few minutes it might be done. I put it in the oven underneath, the hidden oven underneath here. So let's continue on with our proportions. This is a scenario. The scenario is that you are working at a new ready-mix plant. Now you could have been working at a plant that existed for many, many years. But we're here in Salt Lake and we decided to build a new plant. At our new plant, we want to have, a customer says, I need an exterior wall that's 4 stories tall. It's here in Salt Lake, and I need a compressive strength of 30 megapascals, which is about 6,000 years. But across the world, we like megapascals. Other things they told you is that the concrete members, these are the beams, the columns, whatever piece of the structure you have, the smallest member in dimensions is 180 millimeters. Alright? That's a little bit bigger than 6 inches. The structural rebar, by the way, rebar is not part of the concrete, but we put it inside of the concrete. It's like when you bake a cake and you put the little structures inside for that big fancy wedding cake to hold up. So in that case, I have a minimum cover depth that's from the rebar to the surface on any side, or spacing between rebars, between, not center to center, but between, is 35 millimeters. By the way, 25 millimeters is 1 inch, size of your thumb. The finest modulus, I assume you've heard of this term, that came from your lab. In this case, it's going to be a 3.0. And the dry rotted unit weight, we measured it here in the lab, oven-dried condition first, before we rotted it into that bucket, is 1865 kilograms per meter cubed. All of these information will come in handy later. Now here we are at the situation, we need to know how much of each of these ingredients do I batch out to make this perfect concrete for this structure. Now one caveat, again, this is the ACI method, right? This is designed in case you've never made a concrete batch ever before. If you've made one before, you probably are going to go with the volumetric method, where you have an existing design and you're just going to tweak it. But here I'm in a new plant, I'm probably going to not know where to start. You can start here. So in your book, unfortunately, the writers did not do it justice. There is not a very standard procedure well described in here, but I'm going to walk you through it with this handout. The first thing to look at is to figure out, there's 10 steps by the way. The first is to figure out your strength. All right? How much strength do we need? It's in megapascal. What was that number? What is it? 30. Well, I need my design string. This is going to match up exactly. We'll do this for a moment. For step 1, I need to figure out what is my design string. This is different than 30. Because when I want my structure to be 30 megapascals in real life, what I mean is I want at least 30 megapascals. That's what I'm going to assume. I need it to be bigger than 30, my concrete, to make sure that my 2 standard deviations are going to also provide it above 30. How do I figure out my standard deviations?
Trial and take sample.
Trial and error? That might be a long time. These people want to design today. I'm going to suggest your handy-dandy textbook. In here is various scenarios. We have an equation 1, a 7.1, which if you read it, is a standard system where we have the design strength, compressive strength, is going to be a function plus 1.34 s. S is your standard deviation. The FC is this design strength, the lowest one. Okay? Now this is if I know my standard my standard deviation. My cookies never deviate, but some people say they do. This is if you know x. Now, what's if I don't? Let's read 7.2. In this case, it says if I have a large standard deviation, then I have to use this equation. Right? There is a US version, and there is a SI version, depending if you are in Europe or the United States, or other places besides Europe. I still don't know if X. That doesn't help. So I keep reading. Then there's a table that says standard deviation if it's less than 30 samples. If my n is less than 30, do I have a sample set less than 30? Yes, I better believe it. It has a modification. So I need to modify my equation with a factor. Now if it's 15, then I use a modification factor of 1.16, for example, in this test. Right? So if I have 15, then I use a factor that is 1.16. Okay? And that is multiplied by my standard deviation. Still doesn't help. I don't know my standard deviation. Now what do I do? I keep reading. Okay, linear interpolation still works, by the way. If I have 18 samples, for example, I will interpolate between them. I don't have 18. I could try to extrapolate down to 0, but that's crazy. So I keep reading. At the top of the next page, it says, if I have less took off or just forgot to label their tables. Nobody here does that, right? We use the next table. Now it says strength, and there's a different equation for my strength range. What is my strength I need? Right? So that is my F prime C that I'm aiming for. There are two versions in here. There is the metric, or SI, and then there's the US, in parentheses. These tables get confusing. Be careful of the units. Metric is first. Anything in the parentheses is a separate equation if you want to do US units. Okay? It does not multiply all the way across. So if I need 30 megapascals, for me that follows in the middle of that table. You see the table. So in that case, we have an example that says for 21 to 35 megapascals, my equation is F prime C plus 8.5. So now I plug and chug. 30 megapascals plus 8.5 gives me what strength? 38.5 megapascal. I'm going to leave that over here. And if anyone wants a picture, I'm going to take rid of it. Get rid of it. Now it's also good to keep reading the paragraph in case there's other equations. But I've done this a couple times, so I'll tell you on this one, that's the last equation for strength. Okay? Now the next step of the 10 steps is, anyone have that sheet in front of them? Want to tell me? Water to cement. Who can tell me why do I want water to cement ratio? Workability is strength. Correct. If my water cement ratio goes up, what happens? Then my workability goes up, or my slump goes up. What else happens? My strength goes down. Hopefully you saw that in your water there. Now there's a table here, or a figure. So figure 7.3 shows two graphs with strength and water cement. Okay? What are these two curves? Okay? We have an air-entrained admixture and a non-air-entrained admixture. I'm going to ask a question. Which one do I follow? How do I know? Did they tell me in the scenario if I need air and trainer? No. I do not expect my owner to know this. I need to know this as an engineer. When do I need air and trainer? Or rather, what does an air and trainer do?
Doesn't it help with when there's a lot of temperature change?
Sure. Do I have
Or am I-
temperature change? There's a specific temperature range, though. Salt Lake City. That's the temperature range. Yes.
It has a lot of cycles.
Yes. Freezing and thawing. When I have cycles, then I probably need air entrainer. Although, you also have to think about where your structure is. Is it inside, where it's insulated, or is it outside, where it sees the freeze-thaw?
Outside exterior.
This is exterior. And it is Salt Lake City, so we expect freezing and thawing. And we lost our lights. Okay.
No, they're back.
So, we have freezing and thawing. So we are we going to have air entrainer or not?
Yes.
Yes. This is an important middle step here. We need to look at the air entraining admixture information. Now I'm going to go into table 7.1. Finally, they have labeled their tables. In here, it says water cement ratio for different compressive strengths and different air entrainer or non-air entrainer. What is my compressive strength? 38.5. We use the new strength now. Where is that on my table? It is not. Ah! What do I do? Find the what? Find the closest. We could do that. What we could do? Interpolation. You want to be right on the button for your first concrete mix. You don't want to disappoint. Let's calculate. Who wants to calculate? Ooh. Now here's the question. There's two numbers. One says non-air entrainer. The other one says air entrainer. Which one do I use? Air entrainer. So it's going to be between which numbers? For 38.5.
35 and 41.
Oh, yes. We are between 41 and 35 megapascals. For 41, we have a 0.32. And for 35, we have 0.40. For the sake of brevity, I think we should use the cheat sheet. Have you interpolated before? If not, good practice. One minus the other, divided by the other one minus the other, and always have a reference, which is either 35 and 40 that you compare it to. I'm going to calculate that I get 0.35. Now hopefully you see that it's between them. And we can go from there. Questions? All right. Now, are we done with that step? Those of you with books, are we done? No, there's more tables. If you read, it says keep reading all the tables. Let's check the next one. 7.2. This says maximum amount of water cement ratio. And that's if you have strength data from field experience or trial mixtures that are not available. Are we in that scenario? We don't have any on this table. It's not. Ah! Where would it be? At the very bottom. It's not even on the table. If you were to look at it, the numbers are getting smaller. Correct? And there's two asterisks. For strengths above 31, for non-air entrainment, or above 27.6 with air entrainer, the concrete proportions shall be established from field tests or trial mixtures. Oh, shucks. Guess we get to make cookies. And try them out. That's what that says. But be careful. Sometimes it doesn't say that. We also have to check the next one. 7.3 and 7.4. There's two more tables. These are for various conditions. Or exposure levels. Okay? So if you look at one of them, one looks for if it's freezing and thawing, or if it's cold and permeable, if there's de-icing salts put on it. Now we have a wall. It's probably freezing and thawing, yes. And that freezing and thawing category at the top of 7.3 says that we base our strength on our structural requirements. So in that case, no water cement ratio problems. If I go to 7.4, it looks for sulfates. I live here in Utah, which has sulfates in the soil, so be aware of that. I don't actually know how much sulfate I have in my environment, because does it say? I may have actually looked into that before I tested my wall, or got details. And I did not report it. What exposure level would you like to say today? What's it? You want to say low? Moderate? High? Let's go for extreme. Oh, true. We're not in St. George. Let's go with moderate then. Moderate? If it's moderate sulfate, what is my water cement ratio? Good catch. This is a max. Am I below 0.5? What if I was in St. George, where it's very severe? My max is 0.4. I would have been okay. For this design, again for this strength, if you're in a different scenario, it may not be. Now, we go on to the next step. Pictures, anyone? Going on. Pictures? What is the next step on your handout? Number 3 is force aggregate context. What is the first sub-step? What do I need to know about my course aggregate? I need my size. What size of aggregate did I have? It didn't say. Oh no. What size do I need? That is in my table. I have a structure I'm designing. The structural engineer has designed it and handed it I'm going to say C, bottom, table. What size do I need? I have 4 scenarios. Form dimensions, clear spacing between rebar or tendons, clear space between rebar and formwork, and unreinforced slab. Do I have any of those scenarios? I have a form dimension. Do I have any other ones? Between the rebar, and I also have a clear spacing with also the surface or the form. Let's check all of these. Form dimensions. I need 1/5 of the clear distance. What is my clear distance? Sure. Let me continue. Form dimensions. I will put in my form dimension. My smallest form is 180 millimeters. Can I put it in its inches? Well, it's good to keep in the same unit, but I could actually put it in inches as long as I go inches on the other end of it. What is 1/5 of 180? Millimeters. How about the rebar? This is 3/4, and actually they're both the same equation if you read. Times the clear spacing. That, in this case, was 35 millimeters. What is 3/4 of 35? Okay. Do I have an unreinforced slab? No. Okay. What size of aggregates do I need? What are these numbers? What does the table say at the top? Are these exact, minimum, or maximum? Can I use an aggregate that is a 1-inch aggregate? Yes. Yes, I can. Even if it's really close, technically I can. Can I use an aggregate in our lab? Yeah. Which is what size? I felt like it was 3/4 or 19 millimeters. Yeah. By the way, these are nominal maximum aggregate sizes, meaning that that is the first size that's retained. If you want to make sure, you go a little smaller. You want to make sure you meet the spacing requirements. This is here because as I'm pouring my concrete in, if I had a concrete form, a cookie form, go back to my cookies. If I had a mold and I had a big chunk of chocolate chip that was bigger, it's gonna get stuck and it won't go all the way down. I like to take a bite of cookie and chocolate all the way through. So I want enough chocolate bits interdispersed. I need them smaller than this size so that I have them everywhere. I want the rocks everywhere. of your dimensions, and smaller than the distance between the rebar so that it falls through them and continues into the structure. Right? Okay. Now we go on to the still in coarse aggregate project because I don't know how much coarse aggregate I need. How do I figure that out? There's another table in here. 7.5. This one's a little bit trickier. Okay? In here, on the left-hand column, is our nominal maximum aggregate size of our rock. Not what it says you need, but what we decided to choose and use. So we need our nominal maximum aggregate size. It is again written in metric. And in US units. Do we want to use our aggregate in our lab?
Yeah.
Okay. How about our fineness modulus is also on here at the top? What did I say that was? If you ever have one that is not a nice pretty number at the top, what do? Interpolate. Now, I look at my aggregate at 19 millimeters, and I go across till I find 3 for my finest modulus, and I pick up a number. And that says 0.60. Now, helps to read what I'm reading this off as. It says, bulk volume of dry rotted coarse aggregate per unit volume of concrete for different finest modulus of fine aggregate. Whew. This means I have dry rotted unit weight divided by volume of total concrete. This is a volumetric ratio. This means 60% of my entire concrete is going to be coarse aggregate. Now I'm going to take a step here and say, when I was going into my backyard and doing that 3-2-1 shoveling policy, not very accurate, but works, if I did 3 shovels of coarse aggregate, and I have 2 and a 1 of the other 2, what is that volumetric ratio? 50%. Is that even on here, by the way? Not for that aggregate, but it does work. It is in the rim. But remember also when I do the shovel, I add water. Right? That also changes some of the structure. So you can even go less than 50% in some situations. Now these numbers were developed also in 1940, so they're a little old, but they still kind of work. Today, if you had watched the videos, you would see that there's a big push to making this table change and following the tarantula curve method. For now, again, if you're making a new mix design from scratch, this method still works. Gets you in the ballpark. Okay? So we're going to have a 0.60 as our dry rotted unit weight over our volume of concrete. That is our volume of coarse aggregate to concrete. Any other question on that one? Okay. Anyone questions? What is our next step? What does it say now? How much? Whew. How much air do I need in the structure? This one's not provided. Although there is tables, I think. That we will look at. Table 7.6. Which is approximate target air content. A lot of times when we make air, we're trying to create air in the concrete, depending on how you mix it, depending on your air training, depending on the temperature, and the person doing the test. You may not actually hit that target air. But this is the goal that we're going for. So this is a target air amount. It also has, do you want air trainer or no air trainer? Again, we said we did want air trainer in our situation, and it has subcategories of your exposure level. We had said it was moderate. And by the way, that exposure level is for freezing and thawing, actually. But what is our maximum aggregate size? So, on 19 millimeters, what is our target air content? We get 5.0. This is a percent. This also means the volume of air over the volume of concrete. Fair? And this is typical for Utah. If you're in a high freezing and thawing environment, and you still have 19 millimeter aggregate, then we aim for 6. Also very typical in Utah. Right? Now, next step is workability. Now, I would tell you, there's one table here that we're going to start with. And this is comparing the slug that you need versus the type of structure. And again, like before, we have metric and US. Or units. What is our structure? It's a reinforced what? Is it a wall, a footing, a caisson, a beam, a column, a pavement, or mass concrete? A wall. I like reinforced in the name too. Is that reinforced? The first one is foundation walls. So yes, they're probably under the ground. We're going above the ground here. So I'm going to put above ground. So in that case, I would probably go with the 25 to 100 millimeter or 1 to 4 inch slump. Now there's a little side story, I would say, because again these tables were made in 1940. This is before the water reducing admixture was developed. A lot of people will go on the stiffer side, and they will make a stiffer mix and then add water reducer to make it more workable if they need it. So in this case, I would say aim or lower. From practical purposes, we don't want a soupy cookie. Okay? So, before we get down to the next step, I heard a bell ding. Did you guys hear the bell ding? My little timer went off? I think that means my cookies are done. Ding. And voila. Would anyone like a fresh cookie? They've even cooled off already. Yep, cookie break. Come help yourself. Julia Child style. Okay. If anyone would like other cookies while you're coming out, we also have oatmeal bread too. And I have chocolate. Whoever wants oatmeal for the breakfast. I'm trying to keep you all fed. Can't come to a cooking class without cookies. All right. Let's go on to the next one. Yeah? Good cookie break. So our next step is water amount. In this case, there is one table that we primarily look at, and a second one that we have to remember to look at to make some adjustments. So the water amount, we will look at table 7.8. Right? And again, like before, we need some information from before. We use this table uses nominal maximum aggregate size, and it uses slump to create how much water you need. Again, I will mention, this table was developed a long time ago, and it's often the contention for why this mix may not work. But today we tend to stay on the low end if we can, and then we adjust from there later on. So what is my nominal maximum aggregate size? 19. Oh, and it also has one more in here too. Often a sign of issue. It also has an air entrainer section and a non-air entrainer section. Do I want angel food cake or do I want a dense cake? Which one do I need? Angel food cake. Okay. What is my slump?
We're going to go low 1 to 2.
Let's say I'm on the low side. Let's do a 1 to 2 inch. And with a 19 as my nominal maximum aggregate size, what is my water content? And what is my unit? So this is actually my mass or weight of water for a total batch of concrete, or a total volume. Is what that unit means. Okay? Now the tricky part is you have to go back a page. And we have to check our aggregate shape or texture. This is a modification factor. We need to know, is our aggregate, there are 4 options here if you read the description not on the table. There's a subangular. There is a gravel with crushed particles. And there's a round gravel. Now then, if I'm making chocolate chip cookies and I put in the chunks of chocolate chip, they're harder to mix. I don't need as much of the other ingredients to mix it, or any more ingredients to mix it, because it's harder to mix a chunky bit. If I put in a sphere or pretty close to a sphere of a chocolate particle, it's a lot easier to mix it. In this case, that's what we're looking at. How much water do I need to get that workability or slump that I'm aiming for in this system? So in this case, if I'm angular, I use a factor of 1.0. Not on the table, but if you read the text, it says that. If I use subangular, I use 12 kilograms per meter cubed. Or maybe I should even say there. Let's say 0 for a moment. Yeah. These are modifications. Back to this. If I do crushed, I do 21 less. And if I do round gravel, I do 27 kilograms less. So this is water or less water that we put into the system. If those are the situations. Again, if it's round and granular, or a round gravel particle, I don't need as much water to get the workability. So I'll have less water that I put in. Okay? Which system do I have? If I'm using the aggregates from our lab. What makes it a gravel versus an angular? Gravels are often formed from a hard material like granite. They've been polished over time with erosion. When I have an angular, that means I've taken limestone typically, or something softer, and I've crushed it to get it with edges. Which type of rock do I have? We definitely have a limestone rock. I'm going to say for now, let's leave it as angular. After watering that. If you ever worry, we could reduce it to that. Would you like to reduce it? Yeah. Oh. What is our water amount? Good to have assumptions. We see the subangular. I have 168 minus 12. 156. Okay. Questions on that step? There's no interpolation on that. Now, step 7 is my cementitious content. How do I figure this one out?
With the water cement ratio and the water reduces by the
Water cement ratio is water mass or water weight divided by cement mass or cementitious weight. Cement or cementitious and mass or weight. I know my water mass because I just figured it out. How much cement do I have? Algebra. I take cementitious mass as my goal, so I will do a water amount what? 0.7. What is my unit? Kilograms per meter cubed. This is another modification I'm going to tell you, is a cementitious amount. Now, as you had mentioned, in a lot of our concrete, we like fly ash in there. If I wanted to put fly ash in there, I want it to be part of this. So, in my scenario, apparently I want 40% slag. Someone has a supply of slag. Maybe not slag. If it does not say the unit, for something like an admixture, we're going to assume this is a mass percent, or a weight percent. And then I can figure out how much slag I need. How much slag do I need? 178.3. And that's kilograms per meters cubed of concrete. How much cement do I buy? 267.4. How do we get that? Correct. This is not the number I need anymore. I need slag and cement. Okay? And now, yep. So we get the water amount from the previous step, or previous stage, right? We had the water from the table, we adjusted for aggregate, we got 156. So we put 156 and divide by the water to cementitious ratio that came from a previous table. And then we get cementitious. Now if you have no supplementary materials, then that is your cement amount. So in that case, I would match 449 kilograms per meter cubed of cement. But because my owner has specified they'd like some slag in there, then I'm putting slag. Try that number. 156 divided by 0.35. Yeah? Any other questions? All right, next step. We're on step 8 of 10. By the way, some of you may notice there's actually 11 on it. Step 8 is admixtures. Do I have any admixtures that I want to use? We need an air trainer?
Yeah.
Probably. A typical air content, if you don't even try for it, will be about 2%. And I think you actually saw that in your last lab. So that's good. When you add an air trainer, it should bump it up at least 2%. The ratio is about 1% of air content for every, well, I guess it depends on the manufacturer. It could be about 10 milliliters or so per cubic yard. We would go to the manufacturer and figure out the dosage. It is not the amount of concrete you batch, it's how much cement you put in. So in your last lab, your instructor told me you had batched out some different admixtures. And if you looked at your notes on those, you should see that they are either, say, kilograms per, or a dosage of so many milliliters per kilograms of cement, or a certain dosage per pounds of cement, depending on which unit you like to use. Okay? Sometimes it's good to know how much water reducer you need if you need that as well. It's a very common admixture to have on hand. And again, you can look at a manufacturer for those numbers. We will walk through an example in a second. I do want to step to the next one though, which is next step. 9 is going to be a volume balance. So in examples where someone has given you a mix design, or you found one from somebody else, a lot of times they will give you the entire system. It has been balanced based on their source materials and their measured properties, but it may or may not be equivalent to your system. So even when you have one that someone else gave you, you can actually jump in at this stage and you can do the volume balance of your own mixtures. The interesting thing about this method when it was developed is they purposefully left one ingredient out so you can balance the system. One equation, one unknown. Again, one of the downfalls of it is because that one ingredient that you left out may actually be misproportioned in this system. So many people do not like this one after a while. Great for a initial mix, you've never made one. But after making some, most people just tend to do tweaks to it so they get to the system they want. I believe your instructor will go through more of the tweaks next time. Okay? A volume balance. What's missing? What do I have back? What do I know about my concrete mix you have told me goes into my cookie? What do I need?
Water.
I have water. I have cement. I have what else? Coarse aggregate, fine aggregate, air strainer. What else do I need? If I didn't have air strainer, do I have one that I'm missing? On a volume basis. What is it? Air. Which one? Let's start with what we do now. How much water do I need?
156 kilograms per kg.
Okay. How much cement do I need? 267.4. I have the slag too, by the way. 178.3. How much coarse aggregate do I have? I have a problem. I haven't calculated. Let's calculate it. I have, in this scenario, 400 and, oh, not 425, 0.6. I'm going to multiply it by my dry rotted unit weight. Which is given to me. 1865 kilograms per meter cubed. You can tell me what that is. Say it again? 19 kilograms per meter cubed. Now, question. When you did your aggregate labs, what moisture content state is that? This is oven dried mass of my course aggregate. That means this is going to be oven dried condition when I batch this out. So now I have 1119.0 as my course aggregate.
But what are you supposed to do with the ones at the bottom of the concrete?
Oh, good question. This is still my volume of concrete. This is how many pounds or kilograms in a meter cube of volume. So if I need 60%, so I have a volume that's concrete, 60% of the volume must be coarse aggregate. So the weight of that 60% is 1865. Okay? Now, air and trainer, I didn't show you that, but you do it on your manufacturer amounts. Air content has no weight. I can't batch air by weight. These are masses. Weight in this column. The other thing I'm missing is fine aggregate. And so in a volume balance, we are going to learn how to do the conversion between mass and volume based on what property? How do I figure out the volume of these? Specific gravity. Correct. What do I know about specific gravity? What does that equal? Fundamental.
The density of water, or the aggregate divided by the density of water, or unit.
There's a density of water on the bottom. What is on top? Correct. The specific gravity has no units because it's dimensionless. I divide by the same units to get the property. You can do this for any material. Our chocolate chip cookies have a specific gravity. Our flour has a specific gravity. Okay? We have to look it up. For water, what is our specific gravity? 1. I'm going to erase this for a moment, okay? Let's do a column of this. Water is a specific gravity 1. Cement, to look it up, is 3.15. Portland cement. Coarse aggregate, what is our specific gravity? I don't know if I told you. Did I tell you?
Yeah.
Oh, that's so nice of me. Well, there you go. 2.61. How about our fine aggregate? 2.38. We have our air trading admixture. We often use it as water. We use the same as 1. value. Sometimes it helps me, especially after I've had too much wine and too much butter, fat. We have a density. I have to remember that that is mass over volume. All right? How do I figure out the density of the material? Okay. And how does it relate to specific gravity again? It is this top number. What is the density of water? If I like US units, it's 62.4 parts per cubic feet. If I like metric units, 1,000 kilograms per meters cubed. If you like going more crazy, it's 1 grams per centimeters cubed. But we are dealing with those. We like big quantities in our cookies. I like a big batch of cookies. Okay? So, how do I figure out volume? I play with a little algebra, right? I need volume. So let's figure that out. Volume is, let's rewrite this. Mass over density. Now, I don't know density, but I know specific gravity. So this is mass. Now what do I put in for density? Specific gravity, is that by itself or do I need something in there? Times the density of water. Don't forget the water, or you'll be 1,000 off. Yeah? Shall we do this calculation? Or let's do this spreadsheet. So all of you have been provided this by your instructor, which is so nice. Although we did a different number, so we'll go through here and recalculate it. So in this scenario, let's put up the screen. Alright. 156 is our water. Okay. So in this spreadsheet, let's walk you through this. This spreadsheet is set up with all of the materials on the left-hand side in column A, and at the top is different scenarios. We have the initial batch weights, specific gravities, and initial volume estimate. Okay? And then later we'll learn how to do things like SSD and calculating things like stop conditions. That will be step number 10. Okay? And by the way, step number 11 is trial batches, because they did tell us we need to do some trials. We had less than 15 samples. So, which I would actually encourage anyway. We did have from our table course area content. In this scenario, I actually have some numbers that are pre-written down here. We have all of those numbers I had on the board. 38.5 as your design strength, coming from table 7.1 to 7.2, and then also a table on page 249 if you have a certain version of the textbook. The water cement ratio coming from table 7.1 through 7.4 is 0.35. Zoom in here. Our course aggregate to core volume of concrete ratio was 0.6, also from the table. These are great places if you ever needed to use it as a calculator to calculate your interpolation even on this sheet. Okay? Our target air content, also from a table, 7.6. The estimated water, we just said was 156, coming from the table, or if you like to say we had originally 168 minus the 12, if you needed to check it. Again, use it like a calculator. The total cementitious, this one's already preset for you, that we take the water amount divided by the water to cement ratio. Okay? And now we get 445.7. If you don't like them in decimals, you get rid of them. Our binder is another way of calling a supplementary cementitious material. So if we have a binder, maybe we don't know what kind it is, but I know that somebody would like 40%, I type that in here. Right? And that's by total binder amount. By the way, this also works for other binders like asphalt. When we get to asphalt. If you have a water-reducing admixture, in this case, I put in the minimum amount that the manufacturer has. If you look up on their website, they will tell you what the dosage rate is. And again, it's often based on a certain amount of cement. In this case, 100 kilograms of cement. So this water reducer is 300 milliliters for 100 kilograms of cement. The air entrain dosage is how many milliliters per percent air that you're targeting per 100 kilograms of cement. Okay? Now up here, we have the thing calculate for us. It has the volume of coarse aggregate times the dry rotted unit weight. I guess I should also point out that your properties of your material, your aggregates, are also here at the bottom right. Let's zoom in on that. We have the coarse aggregate and fine aggregate. If you ever need another one, you can add a row in between, for example. We have the absorption capacity. You learned about that once upon a time. The surface moisture, which is the total moisture minus the absorption capacity. Then we have the dry rotted unit weight that you had done. I do not have it for the fine in this situation because we didn't actually need it for this mix design. The fineness modulus I have for the sand. Again, we did measure it for the course, but I did not put it in here. And these numbers are not actually the same as your lab, but they are really nice for doing this example. Okay? So in this case, again, the spreadsheet, if I zoom in on the top here, is calculating C20 times H20. So if we scroll down, C20 is where the volume of coarse aggregate to volume of total concrete is, and H20 was the dry rotted unit weight. Correct? And again, remember, these are oven-dried conditions, so we will do a moisture adjustment later. Now the cement amount, I usually typically calculate after I've done any supplementary materials. So we'll start with the slag. I have 40% times the cementitious amount. Right? And then this is doing the total cementitious amount times 1 minus the percent of binder 2. That's what this calculator is doing. If you have other binders you want to add, make sure that you add those as extra lines and accommodate it correctly. The water, I'm actually just going to tell it to read from below as 156. And then the water reducer here, I have the 300. You can make that a fixed number. We read the amount the manufacturer needs times the cement amount divided by the 100 to get the correct units in conversion. And the air entrainer, in this case, I also need the cement amount divided by 100, and I need the total air content as a percent. So here I need 26 milliliters of air entrainer. And again, if decimals are an issue, maybe you like 3 sig figs. You can always lower them so you get to your 3 sig figs, or adjust it. Questions on that? So now volume estimate. I've actually typed this in for you, but I'm going to walk you through it. In this case, I've erased it, but it is the mass divided by the specific gravity divided by the density. So I have the mass divided by the specific gravity and then the density of water. In this case, the spreadsheet has it as a separate page. You could just write 1,000, but in this case, it's referring to a bunch of calculations on the back. We have 1,000 here. Okay? 15. So C15 on conversions page is that 1,000. It is very typical in a mixed design like this to have small decimal places because we are doing this for 1 unit or 1 meter cube of concrete. You would expect them to be smaller than 1. Now, as a different scenario, if you ended up doing the US units all the way through, treated pounds per cubic yard, you will see that you're also aiming for 1 cubic yard here. The trick will be, though, the unit for density of water that I gave you is in pounds per cubic feet. So when you do the conversion, you'll actually get, back here, you'll get all of these numbers to be greater than 1 because you're going to go up for 27 cubic feet as your total. That means 1 cubic yard. So if you do the US system with pounds, you should be aiming for a total of 27. And if you're using the metric unit, you will have a total of 1. Okay? Now all of these is just click and drag, like maybe you've learned, just to carry them down. Another thing I'll point out, water reducers, air entrainers, and other admixtures are done in milliliters. They're not 50 bits. 26 milliliters is very small for a cubic meter of concrete. These are small numbers. They're almost negligible. In real life, most people don't even bother to calculate their value. If you'd like to be really accurate and precise, things for like concrete canoe, when they want the real numbers, make sure you put them in there. Okay? But if you can see, they're like 10 to the negative 5th. They mean nothing. They don't matter. I can put 0 and it won't change my number. Okay? Now here's the other trick. I need to put the air content in here. If you forget the air, you are going to be significantly off. It is not a mass. It doesn't have specific gravity. It is a volume. Make sure you always account for the air. Okay? And now with the ACI method, the only thing that's left over is the fine aggregate amount, or the sand. So in order to calculate that, how do I do that? Your spreadsheet. What's that? You can guess. What do you guess it is? 0.2. We're close. What am I aiming for? How do I know if I'm there? I should have a 1. There's 2 ways you can do this. I can say equals 1 minus what's left, but I'm going to get a weird thing. Ah! It's a circular reference. Doesn't like it. Let's get out of our circular reference. The other way you can do this is you can go up to data, and there's a thing up here called what if analysis. I'm going to click on it and say goal seek. Now, it's doing a solver function, just with one unknown. I'm going to set a cell, my target, to a value. I'm going to say I like it to be 1 this case. Again, if I do US units, I should be 27. Now I'm going to change my volume estimate. And I'm going to hit OK. I'm going to push to 1. And it becomes 1. Yeah? Then, now I got to calculate the mass of it. Now I do the reverse of that equation that once was up there. What is that equation again? This one's going to be volume times specific gravity times the density of water, which is over here in the back, 476. Now, if you ever get funky and oh, well, that didn't happen, right? This is perfect. I love this. It's great. Huh?
I was just wondering.
Oh, we didn't take the numbers. That's made it sound really funny. That's not good. But it's live and it edits on it correctly. We can also go back to goal sync again. And because they're all linked, this is another interesting trick. You can set this cell still to 1, still our target. But now instead of changing the volume, I'm going to change the max. And it doesn't like me. So let's try that again. Let's set that one to a 1. Maybe we'll try no. And it still can optimize it. Like 519. Now when I report mixed designs, we do tend to like 3 sig figs. Or you can always have more if it's greater than the decimal place. You know, like 1119 is okay in 3 sig fig realm. Yeah? Questions? I will save the batching stuff for next time if you'd like. Unless you'd like to see anything else today. We're at 8:45 roughly right now. Today I'd like to have time for you all to do your high strength competition and to test your cylinders for those that were here today. Would you like a preview of what's coming up? Okay. So in the rest of this spreadsheet, what we do in this column is we adjust for saturated surface dry condition. Because when I report mixed designs, I tend to actually report them in SSD state if I'm writing a report to somebody. You've learned how to do that when you did your aggregate lab. So we will just put it into the spreadsheet. You adjust for the coarse aggregate and fine aggregate, and the amount of water that maybe you add, because it went from dry now to wet, the amount of water that went added into the weight of the aggregate gets subtracted from the weight of water you fed. Equal amounts. The more the aggregate increases in weight to get to SSD, the less water you need to put in. Okay? All other numbers, slag, cement, water reducer, everything else stays the same. Now, the last two are if you want to batch something other than 1 cubic meter. We need to have a big structure in this case. 3 stories tall wall. We need to get our dimensions of how much concrete we need to batch. We will throw that in here, volume desired, and we'll set up the spreadsheet so that we can batch for a different amount. The actual volume we need to batch. And then the last column is that if I want to adjust for stock weight, because maybe I want to batch it straight out of the bin instead of at SSD, especially for that pesky little set. Right? So we can do the same thing again, adjusting for stock. And that's the rest of your spreadsheet. We typically do trials. We batch something, try it out. If it doesn't give us the properties we want, there's some tricks that people use on how to adjust a mix when it's not working. Your book talks about these adjustments. If you look into section 11, talks a little bit about them. And then I will also introduce you to 7.1.2 is if you're doing small batch jobs, like what we did in our class last time. These are designed for concrete coming through a concrete mixing truck. Big truck that has 10 cubic yards or so. Our batches are very, very small compared to that. Usually somewhere around the order of 0.5 5 cubic feet or something. It's really small. It's typically what we can batch in our drum. If you want to batch 1 cylinder, that's a very small volume. If you also want to batch 1 cylinder with high strength concrete, be aware that it's not only a small volume, but things may act differently when they're in small quantities. And when you design for water cement ratios very low. If you go back to your water cement tables that are in here, they do not go very low. I think the lowest is 0.3. If you'd like to tread lower than that, you can. Concretes have been made with smaller water cement ratios. In that case, there's other resources out there for designing high strength. And these ACI procedures designed for normal concrete from the 1940s. Today we try all kinds of crazy stuff. We like fun cookies. Thank you, everyone. I have more cookies if you like some. Oatmeal. We can take a little break and we can go convene in the lab.